Welcome to this concept explainer brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we are undertaking a deep dive into a really tricky concept from Unit 7, alternating current. We're looking at AC voltage applied to an inductor. Our goal is to make sure this explanation is simple, memorable, and absolutely safe for your board examinations.
Right. This is the topic where things start getting complicated, with the phase shifts and all that. It's where the voltage and current stop moving together perfectly.
Precisely. And that's exactly where we'll start. Let's jump right into a situation you've probably seen 100 times. Think about your home. When you switch off something simple, like an old light bulb or maybe an electric heater, it turns off instantly, right?
Yes, of course.
Yeah.
The light goes out, the heater stops, it's immediate.
Okay, now compare that to when you switch off a heavy appliance that has a big coil inside, something like a ceiling fan or a motor. Why is it that when you flip that switch off quickly, you sometimes see a little flash, a small spark, right at the switch?
Oh, that's true. I have definitely noticed that spark, especially with the fan regulator. If you turn it off too fast, it feels like something is fighting back. Is it some kind of stored energy?
That flash is the inductor, the coil, fighting that change. It's resisting. And here's the really counterintuitive part. We are discussing a component today, the pure inductor, where current is flowing through it continuously, yet the average power it consumes over a full cycle is exactly 0.
Wait, how can that be? There is current, there is voltage, but it doesn't add to the electricity bill. That seems to go against everything we learned about resistors.
It does, doesn't it? And that contradiction is the absolute key to understanding the inductor. We need to find out why this happens. So let's get to the core idea. The most fundamental thing to remember is that a pure inductor resists the change in current flow, not the current itself. It's all about resisting acceleration or deceleration. It has, for lack of a better word, electrical inertia.
So it's not about how much current is flowing, but how fast that current is trying to change.
Exactly. When you apply a voltage to push the current, the inductor fights back. It creates a back EMF that pushes in the opposite direction. This resistance to change causes a delay. By the time the current finally gets going and reaches its peak value, the voltage that caused it is already past its peak.
Okay, I think I need an analogy for this.
Of course. Think of trying to push something extremely heavy, like a huge cylinder of honey, through a long pipe. The pressure you apply is the voltage. The flow of the honey is the current.
Okay, heavy honey. Got it.
When you apply maximum pressure, that's your voltage peak, does the heavy, sticky honey start flowing at full speed immediately?
No, definitely not. It would take some time to get moving. It has so much inertia.
Precisely. There is a delay between your maximum push, the voltage peak, and the honey reaching its maximum speed, the current peak. In an inductor, that delay is a perfect 90 degrees, a quarter of a cycle.
That makes sense. The inertia causes a lag. But why is the power consumption 0 then? Pushing that heavy honey must take energy.
Excellent question. And this is where the analogy helps us understand the delay, but we need to go a bit deeper into the physics. The inductor isn't like friction, which turns energy into heat. An inductor stores energy. It stores it temporarily in a magnetic field.
Ah, so it's not dissipating the energy as heat, it's just borrowing it.
Exactly. It's like stretching a perfect spring. It resists you, it stores the energy, but then it gives all that energy back when you let go. It's non-dissipative.
Okay, storage and return, not usage.
Now, for a mental image to lock in that 90-degree relationship, imagine a very large, heavy pendulum swinging back and forth, no friction. Voltage is the force you use to push the pendulum. Current is the speed of the pendulum.
Okay, force is voltage, speed is current.
When is your pushing force at its maximum? It's at the very end of the swing when you're trying to reverse its direction.
Right. And at that exact point, the pendulum is stopped for a moment. Its speed is 0.
Exactly. So when force or voltage is maximum, the speed or current is 0.
And when is the pendulum moving fastest?
Right at the bottom of its swing, maximum speed. But at that point, you're not pushing it anymore. It's just coasting on its own momentum. So your force is 0.
So they are out of sync. When one is max, the other is 0.
Perfectly out of sync. By exactly a quarter of a swing, that's your 90-degree phase shift, the force is always 90 degrees ahead of the speed. Voltage is 90 degrees ahead of current.
So just to be crystal clear, the current only hits its maximum value after the voltage has already hit its maximum. And this delay is always a quarter of a cycle.
Always. Exactly 1/4 of a cycle. Now that we have this mental picture, let's see how NSERT formally defines this relationship. What does the textbook say?
Okay, let me read it. It says, a comparison of EQs, 7 0.1 and 7.12 for the source voltage, and the current in an inductor shows that the current lags the voltage by 2 or 1/4 14 cycle.
Perfect. That's the exam safe statement. Current lags voltage. Now let's quickly break down the maths behind why this happens. We always start with the applied AC voltage, which is a sine wave, V equals Vm sin omega t. But the physics of the inductor, from Faraday's law, tells us that this voltage is equal to L times di by dt.
So the voltage is proportional to the rate of change of the current, not the current itself.
Yes, and that is a whole story right there. If the voltage is a sine wave, then the rate of change of current is a sine wave. To find the current I itself, what do we have to do mathematically? We have to integrate, and when you integrate a sine function, you get a negative cosine function. And a negative cosine is just a sine wave that's been shifted.
Shifted by minus 90 degrees.
Precisely. The calculus forces the current to be I equals m sin, omega t minus 2. That minus 2 isn't a guess. It's a mathematical result of the inductor's physics. The text also gives a name to the opposition to current flow. What is it called?
It's called inductive reactance, and it's written as XL.
Right, and the formula for it is?
The formula is XL equals omega L.
Fantastic. And you can see this reactance, XL, it acts just like resistance in Ohm's law for the peak values. M equals Vm divided by XL, and its unit is also the ohm. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is PROSAM.com. Now let's look closer at that formula. XL equals OL. This is so important. Unlike a resistor where R is just a constant value, XL depends directly on the frequency.
So if the frequency is higher, the opposition from the inductor is also higher.
Much higher. It means the inductor is really good at blocking high-frequency signals. Let's take a tiny example. Say we have an inductor with L equals 0.1 Henry, and the frequency of our main supply is 50 Hertz. The angular frequency, omega, is 2 pi f, so that's 100 pi. This means the reactance, XL, is about 31.4 ohms.
Okay.
Now, what if we double the frequency to 100 Hertz? Omega also doubles.
But XL must also double.
Yeah.
62.8 ohms.
You got it. The opposition changes with frequency. This is a huge deal. It's why inductors are used as filters or chokes. They let low frequencies pass through but act like a wall to high frequencies.
So this is the first time we're seeing a component whose opposition depends on the signal itself.
Yes, and it's the first component that introduces this phase angle. This directly leads us into LCR circuits, where you have the inductor and capacitor fighting over what the final phase angle of the circuit should be. All right, let's talk about some common mistakes. The silent killers that can cost you marks in the exam. Misconception number 1 is about DC current. Students often think an inductor offers some kind of resistance to DC.
I can see why. They just think inductor means opposition.
Right, but what is the frequency of a DC circuit?
It's 0.
Exactly, and since XL equals OL, if omega is 0, then XL is also 0. So for DC, a pure inductor acts just like a piece of wire. A short circuit, no opposition at all.
Okay, so higher AC frequency, higher opposition. DC means 0 opposition.
Good. Misconception number 2 is the phase angle. Some students think because it's opposing, the voltage and current must be 180 degrees out of phase, like completely opposite.
Right, pushing directly against each other.
But they're not. They are 90 degrees out of phase, perpendicular. It's a very different relationship. And the third and most critical misconception is about power. The wrong idea is that since current is flowing, power must be consumed. The inductor must be getting hot.
Which we already said is wrong.
It's wrong because the inductor only borrows energy and then returns all of it. In 1/4 of the cycle, when the magnetic field is building up, power is positive. The inductor takes energy from the source. But in the next 1/4 of the cycle, as the field collapses, the power becomes negative. The inductor gives that exact same amount of energy back to the source.
And because the positive part and the negative part are perfectly equal, the average over a full cycle is 0.
Precisely. That's why the current is sometimes called wattless current. It flows, but it does no network.
So just to summarize the corrections, XL increases with frequency, the phase is 90 degrees or perpendicular, not opposite, and the average power is 0 because the energy is just borrowed and returned.
You've got it perfectly. Now let's lock this into our memory. The best mnemonic for inductors and capacitors is EL the Iceman. For today, we just need the first part. ELI. For an inductor, LE, which stands for EMF or voltage, comes before I, the current. ELI. Voltage leads current.
ELI, the Iceman. Okay, that's easy to remember. E before I for L.
Our catchy phrases: inductor, voltage leads current by a quarter turn. A quarter turn is 90 degrees, and here's a physical gesture you can do. Hold your forearm out flat. That's the current, I.
Okay.
Now rotate your fist upwards by 90 degrees. That's the voltage, V. You can physically see that the voltage is ahead of the current. That's the inductor phase relationship.
I like that. Current flat, voltage up, 90 degrees ahead. I'll remember that.
And for one last memory hook, just remember that spark at the switch. The inductor fights back with electromagnetic fury when you try to change its current. It's that sudden release of stored energy that causes the spark. So, to summarize everything for your exam, here are 3 solid factual points. First, the voltage across a pure inductor leads the current through it by exactly 90 degrees, or pi by 2 radians. Second, the opposition to current flow, called inductive reactance, or XL, is directly proportional to the AC frequency. The formula is XL equals omega L. And third, the average power consumed by a pure inductor over a complete cycle is 0. It only stores and returns magnetic energy. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is ProfSam, right?
Yes, ProfSam.com. Keep studying hard, and we will see you for the next deep dive.